All right, welcome back. Here we are. We're going to do a little Doppler effect problem that's very straightforward. This is probably the most traditional question that they can ask about this. So let's build some basic ideas here. If you missed the Google Meet before, I would encourage you to really go and watch that lecture first before coming and doing this problem. But most of you are there, and let's do a problem that's pretty straightforward. We're going to have the speed of sound be 345 meters per second. That really depends on temperature, but for the given temperature on that day, that's what we'll say the speed of the sound was. We're going to have a car coming down the road and honking its horn, and the sound that it's emitting that would be heard if nobody was moving, if the car wasn't moving and you weren't moving and everybody was just standing still, you'd hear 1200 hertz. So you're not going to hear that because people are going to be moving. So let's see who's moving. So the car is moving towards a stationary observer, and the car is moving at 35 meters per second. So I think when you read these questions, the way they word it and where they put the numbers can throw people. It's something you just got to be really careful when you read it, because the 35 is right next to the word observer, and like a quick look, you'd think, oh, the observer is moving. But the reality is, you read the question carefully, a car sounding a horn is moving. So it's the car that's moving. It's moving towards an observer. It'd be nice if they wrote stationary observer, but they didn't. In any case, the 35 meters per second is associated with the car. That is the source. So it is the source that's moving. So on the IB equations, this is the one we're going to want, moving source. Here, F is the sound you would hear if nothing was moving. And here, F prime is the sound that we will actually hear. You have to pick whether to put a plus or minus down here using your knowledge of fractions and the fact that if the denominator gets smaller, then the fraction gets bigger. Or if the denominator gets bigger, then the fraction gets smaller. And that reverse thinking makes it so that when I show this in class, I often put a minus over a plus down here just to remind you, remember you're messing with the denominator. In any case, as it is approaching. So there you're standing there, this car is coming towards you. Hopefully you'll move out of the way, but you're not going to hear 1200. You're going to hear a higher note, a bigger note, right? Because it's going to be higher pitch because of the Doppler effect of it coming towards you. So if this number needs to be bigger because it's approaching, then we're going to put a negative down there. And then B, as it recedes away, so I guess you stepped out of the way, it went back, it went by you. And then as it's far away going away from you, you will hear that sound where instead the tone will be lower because it's going away from you. And you've all had this phenomena, like a car comes screaming by and you're like, and you hear that change in tone. And it happens just as it goes by you, where it goes, and that change in tone that you're hearing is because of the Doppler effect. High as it's coming towards you, and then low as it goes away from you. And it's not just the car changing gears every time. Oh, there's somebody else change gears right then. No, the engine's just going along, doing the same sound the whole time. You're the one hearing a different sound as it goes by. I like doing that. Anyway, I'm going to turn this off because I'm done going. So let's do these. These are very straightforward. We just got to plug in. This is for both of them because this is looking at the next part. We're using the top equation here, and we're putting a minus when it's towards you, approaching you. And by putting a minus, the 1200, that looks like 17. It's bad writing. That's 1200 becomes 1335, rounded 1300. This is when it's going away from you. You put the plus 35. And it looks like it drops down to about 1100 hertz. So high to low as it goes by you. What's happening as it goes by you is more complicated, and we have to look at the component of the velocity that's going towards you. And that could make a good IA or something, but it's not actually in the curriculum. Okay, the next thing I ask you to do is play with this screen, the demonstrator that I was showing you in the lecture before. So if you haven't yet done that, like that's super important to do. And playing with this helps you think about, well, look, the source is moving, and sure enough, when the source is moving, I'm seeing wavelength changes, right? I see wavelength changes. Here's the wavelength, and it's changing. If instead the source isn't moving, if I wait a second and we see that all these wavelengths are now the same, if the observer is moving, it might hear a different pitch just because the wave fronts are hitting it at a different timing, right? Here it says waves as observed, right? So if you're going towards, if the observer is moving, the wavelength isn't changing, but the frequency is still going higher because you're hitting the wave fronts more often. And that helps us to answer the question that is next. Notice the wavelengths only change when the source is moving, which was question C, in which cases is the wavelength actually changing. So a frequency can be observed changing without the wavelength actually changing because of the relative velocities of the observer moving. Okay, D asks you to redo the problem with the car not moving, I guess. Now redo the horn at the non-moving observer and the listener being in the car. So I guess you had two cars, one car's honking the horn and the listener is now in a car that's moving, and again at 35. So now we're going to use this lower equation, the moving observer. This one's a little more straightforward. You're going to get, when they're going towards, you use the plus because you're messing with the numerator. So if you want a bigger number, right, you get that. And you'll notice the rounded answers end up being the same. But if you look carefully at the numbers, they are not the same. And it matters when you have a medium, whether it's the car that's moving or the observer that's moving, and you can get slightly different numbers depending on how many sig figs. It's not tremendously different, and so since we only had a couple sig figs, they round to being the same, but they're actually different when you're moving through a medium, whether it's the observer moving or the source moving. You recall that with light, when we do these equations with light, we learned that it doesn't matter which one's moving, and that's because light doesn't require a medium. And so that's a completely different idea in terms of the Doppler effect when you're doing light. Anyway, pretty plug and chug. Take the time to actually plug it through your calculator yourself so you're practicing not making silly mistakes with your parentheses and stuff. You can mess these things up. Hopefully I didn't. But in any case, that's pretty straightforward and initial beginnings of understanding the Doppler effect. Thanks a lot.